We've talked about water running across the Earth's surface. Now we're talking about water in a different form, of course, because glaciers are made of water, but frozen water, so ice. Glaciers are pretty good at shaping the Earth's surface. They are effective at moving Earth material. Not as prevalent as running water, just because there's not, as many glaciers as there are rivers, but they are very good at moving material. So we're going to start with just our definition of a glacier. It's a thick mass of ice that forms over hundreds to thousands of years by the accumulation, compaction, and recrystallization of snow. So when it snows, you probably know the snow is typically, it can vary in quality. Sometimes it's very powdery and dry. Sometimes it's a little bit more wet and thick. But regardless, usually it's not a solid mass of ice. Like you go out and you can scoop up snow, you can compact it together, you can see individual flakes. Over time, when snow piles on top of itself, it recrystallizes underneath the weight of the additional snow, and it forms a solid mass of ice. Now, even though we don't necessarily have like glaciers in New Jersey, you can start to see this process sort of occur in instances where maybe it's snowed and then it stays cold for a pretty long time and the snow like solidifies into one solid icy sheet. That's sort of like the same thing on a much smaller scale. Glaciers are part of two Earth cycles, the hydrologic cycle, of course, because water is what glaciers are made out of. So when water is trapped in a glacier, depending on the climate at the time, it can stay in that glacier for tens to thousands of years. And this is because glaciers are large, so while they are sensitive to changes in climate, they're not going to melt immediately when temperatures warm. So glacier ice is going to remain for a pretty long time. The other part of the Earth cycles that we see glaciers prevalent in is the rock cycle, because they're, like we said, really effective at moving rock material, creating sediment, and transporting it through erosion, which we know is part of the formation of sedimentary rock. Now, there's two main types of glaciers. The first are valley or alpine glaciers. These are ones that exist in valleys, and they flow down valley from an accumulation center. So these are like the giant rivers of ice that are going to flow down a mountain. Ice sheets, on the other hand, are larger scale. They exist in the polar regions of the world. So currently we have two major ice sheets. We have one in Greenland, which is in the northern hemisphere, and we have one in Antarctica, which is over the South Pole. So the world itself looks kind of like this. And these lines of latitude go all the way across the Earth, with 0 degrees being at the equator. If you go up here to around 66.5 degrees north, this is something called the Arctic Circle. And if you go down to 66.5 degrees south, you have the opposite of the Arctic Circle called the Antarctic Circle. Now, at these latitudes between 66.5 and 90 degrees north and south respectively, there are periods of the year where there's no solar radiation, no sunlight hitting at these areas because of the tilt of the Earth. So there's times during the year where they get no sunlight. At other times of the year, they get a lot of sunlight. However, they almost never receive direct sunlight. So it's always really cold in these areas. These are our polar regions. So in order for glaciation to occur in the form of ice sheets, you need to have land in polar regions, because it's the only places where temperatures are consistently cold enough for ice sheets to form and then to remain. Valley and alpine glaciers can form at different latitudes because the elevation of the glacier reduces temperature enough. But at Earth's surface, to form ice sheets, you need land in polar areas. So we have land up here, we have Greenland, and down here we have Antarctica. Antarctica is positioned over the South Pole. Greenland is not positioned over the North Pole. There's no land positioned over the North Pole. But that's where we have our two ice sheets. This is an example of a valley or alpine glacier. So you can see the mountains there, and then you see essentially this river of ice, right? That's how glaciers are described. My daughter is a huge Frozen fan, and they talk a lot about how glaciers are like rivers of ice. And you can see it, like it almost looks like a river. You see the flow, you see the direction it's moving, you see the sediment that is encased within. And then these are sort of like the banks. That's just mountain valley walls that hold the glacier in its channel. This is an example of the ice sheets that we have. So Greenland's ice sheet is a lot smaller than Antarctica's. Of course, the Antarctic ice sheet is our largest. This circle here is the Arctic Circle, and then there's the North Pole. So Greenland is positioned slightly south of the North Pole, whereas Antarctica is positioned right over the South Pole. Now in these maps, you'll see glaciers, the ice sheet itself, and then you'll see sea ice, or the ice shelf, where the water, or rather the ice extends out into the ocean. Glaciers by definition are anchored to the ground. So if you have ice in the ocean, that is not a glacier. That's sea ice. It's different. In order to be a glacier, you have to be anchored to actual ground. All right. 18,000 years ago, ice sheets covered a lot of North America, Europe, and Siberia. This was known as the last glacial maximum. Over the past 2.6 million years or so, ice sheets have advanced and retreated multiple times. We've gone through periods that we call glacial and interglacial periods, where we've had a lot of ice, less ice, just due to some normal variation in Earth's climate. We have times where it's a little bit colder and the ice sheets advance, and we have times where it's warmer and the ice sheets retreat. The Arctic Ocean itself is covered with sea ice, which is frozen seawater, not glacial ice. Sea ice is up to 4 meters thick, while glaciers are hundreds to thousands of meters thick. Sea ice expands and contracts seasonally. Glaciers themselves form on land. Greenland and Antarctica are both there. You can see the differences in their sizes, 1.7 square million kilometers versus 13.9 square million kilometers. So Antarctica is obviously our largest glacier. Ice flows out in all directions from one or more snow accumulation centers. Now, in the polar regions, there actually isn't that much snow. They're both deserts. Antarctica is the world's largest desert, because a desert, as we'll learn by definition, is an area that receives minimal precipitation every year. So it doesn't snow very often in Antarctica, but when it does snow, it just like almost never melts. So any snow that falls accumulates over millions of years because it never gets warm enough for the snow to melt. So even though it doesn't snow frequently, there's a lot of ice there. And same thing in the Arctic Circle. It doesn't necessarily snow that much, but when it does snow, the ice is going to stay for a long time. Ice shelves are going to be the areas where glacial ice starts to flow into the sea. So this is sort of like the barrier between a glacier and the sea ice itself. Along parts of Antarctica, the ice flows outwards from the land and into the sea, creating ice shelves. In shallow water, the ice is going to be grounded to the bottom of the sea floor, but in deeper water, the ice sheets will float, and then they're going to start to break apart, creating like icebergs and other floating objects out there. Okay, they're thickest on the landward side, thinner seaward. Some ice shelves are unstable and start breaking apart, and breakup of ice shelves is attributed to trends related to accelerated climate change, which we're going to learn more about climate change soon. So this is an example of what an ice shelf might look like. So you have a glacier somewhere back here. It starts entering into the ocean, at which point it's changing into an ice shelf. It's grounded here, but once it gets deeper, now the ice no longer connects with the bottom, so that it starts to float, and then it starts to break up a little bit more easily, because it's not, hundreds of meters thick anymore. It's a thinner layer, so it's going to break apart at the front, or it's going to melt, and that sea ice will decrease in that area. This is an example of an ice shelf in January of 2002 versus March of 2002, so you can see the difference in where the ice has begun to melt and break apart. Other types of glaciers also exist. Ice caps can cover some uplands and plateaus. Ice caps are similar to like an ice sheet, but it's just a smaller scale. And again, they're going to form in areas of increased elevation. Ice caps and ice sheets feed outlet glaciers, which are like little tongues that extend outward. Those are the valley glaciers that kind of connect to a larger sheet. We also have something called Piedmont glaciers, which form when one or more alpine glaciers emerge from a valley and spread out. These are going to look actually very similar to alluvial fans. The only difference is alluvial fans are when channelized water reaches an outwash plain and then spreads and deposits its sediment. So the Piedmont Glacier is going to look similar, but it's just that it's a glacier. So it's going to run through a channel and it's going to reach an opening, so it's going to kind of spread out the same way that water would, just only as ice. So this is kind of what they look like. This is a Piedmont Glacier. So hopefully, if you recall what the alluvial fans look like, this looks very similar, and you can start to maybe visualize how this process would occur. In this instance, it's not water carrying sediment, it's just ice moving through. It's just not confined to a channel, so it's going to spread out. All right, now as far as where glaciers form, glaciers are going to form in any area where more snow falls in the winter than melts during the summer. Snow above the snow line does not melt in the summer. Snow lines are going to vary depending on where you're at. Glacial ice formation happens when air infiltrates snow. Snowflakes become smaller, thicker, and more spherical. Then the air gets forced out as snow is recrystallized into a denser mass of small grains called firn. Once the thickness of the ice of the snow exceeds 50 meters, the firn fuses into a solid mass of interlocking ice crystals that we call glacial ice. Again, it's very similar to the process that forms detrital sedimentary rocks. In detrital sedimentary rocks, you have this collection of pieces of sediment, and then under weight of overlying sediment, they sort of fuse together through this process of compaction and cementation. Same general idea. The snow is going to pile up, so then at the base, it's going to get fused together into a solid ice sheet. Icy mass, whatever we want to call it. Glacial ice itself is going to flow. It moves in two ways. The ice itself actually moves. It flows like a river, but more slowly. And that is plastic flow. So within the ice, it is able to actually flow. And then the entire glacier just also slips downhill. So you're moving the whole mass of ice down the hill because, ice is slippery. So it's going to move downhill. And then within the glacier, the ice will start to stretch out in areas where there's reduced friction, and it will move more quickly. And then areas like in contact with the valley walls will move a little bit more slowly, just like we saw in the flow of rivers. Glaciers, like rivers, are going to move fastest, typically in the center, and they're going to move a little bit slower along their edges. When it comes to basal slip, having the whole ice sheet move down the mountain, the meltwater that is created acts like a lubricant, and it makes it more slippery and moves it a little bit faster. However, I say faster, but glacial movement is very slow, right? You ever heard the expression like, oh, we moved at a glacial pace? Like, it's very slow. It doesn't happen quickly. You can't typically observe it in the moment, but you can track it over time. So this is showing us, here we have the entire mass slipping downhill. And in addition, the ice itself is stretching and moving and flowing. So if we add up the combination of how much it moved downhill together and how much this stretched out on its own, you'll get the total movement for that particular area of the glacier. Ice itself behaves brittle until it's subjected to pressure due to the weight of at least 50 meters of overlying ice. So in contrast with the lower plasticky portion, the upper zone is brittle and therefore fractures much more easily. This forms what are known as crevasses, which are cracks in the ice. They're present in the zone of fracture, but sealed off by plastic flow at depth. So if you've ever, watched a mountain climbing movie, they talk about like a crevasse. It's essentially, I'm trying to give you like a good description of what it could look like. I don't know, nothing's really coming to mind. The only thing that's kind of coming to mind, such a weird description, but like sometimes in like sourdough bread or other types of breads, the crust, the outer part will have like cracks in it, but if it doesn't go all the way through. So if you like put your hand in the crack, it would stop and it would be sealed off at the bottom. That's sort of what the crevasses are like. The outer part is brittle, so it's going to crack open, but then it's sealed underneath because of that plastic flow, since the ice there is under so much more pressure. So like this guy right now standing in this crevasse, probably not the most advisable thing in the world. I'm assuming he's a professional. You can fall, they can be pretty deep, but they do eventually end where the ice is more solidified at the bottom. They can also serve as channels for meltwater, so that can rapidly fill the crevasse and move forward down the mountain. All right, movement of glacial ice is not obvious. Like a river, glacial ice does not all move at the same rate. Flow is fastest in the center. Valley walls and the floor slow the base and sides, causing drag. So I could just describe to you. So just like a river, it's going to flow fastest in the middle where there's the least resistance, the least friction. If you're rubbing against or scratching against rock on the walls or on the bottom, you're going to be slowed down. Glacial velocity can range from extremely slow to a few meters per day. Some glaciers exhibit extremely rapid movements called surges, rarely, and rates of movement have been measured using markers in the past, and presently we use other remote sensing technologies like time-lapse photography or GPS sensing. So this is an example of how we used to measure glacial movement. Here, this surveyor laid out stakes in the year 1874, and they lined them all up in a straight row, and then over time they could track how far the glacier has moved. So along the valley walls there was less movement, and in the center the glacier moved a lot more. So you can see that over that 4-year period we had pretty significant movement, and then same over the next 4 years from 78 to 82. What we also see here is what is called the terminus of the glacier. So these lines are showing us where the glaciers ended in these different years. So in 1882, the terminus of the glacier was right here, despite the fact that the terminus in 1878 was here, and in 1874 was here. So truthfully, what is happening to this glacier? Is it moving forward or moving backwards? Yeah, it's retreating, right? Because it used to end here, and now it's ending here. But these are still moving forward. And that's because when a glacier retreats, it's not actually moving backwards. It's always moving forwards. It's just that a lot of it is being lost to wastage. So there's melting occurring that is reducing the overall size of this glacier. So even as it travels forward, it's being like reduced in size. So it looks like it's going backwards, even though it's like a conveyor belt. It's always actually still moving forward. So the flow will always be downhill, but if more of the glacial ice is lost to wastage than is replenished, it will appear to retreat. All right. Now, these are some vocabulary terms that have to do with the budget of the glacier, and this is kind of what I just described. The zone of accumulation is the area where the glacier forms. It's what's located above the snow line. The zone of wastage is the area where there's net loss of glacial ice. The glacial movement is going to be determined by the budget, just like any account. If you're adding more than you're taking away, the balance will grow. So if you have more accumulation than you have wastage, the glacier will advance and in size. It will appear larger than it was before. If you are taking away more than you're putting in, your balance is going to decrease. So if you have more wastage than you have accumulation, the glacier will appear to get smaller in size. It will move backwards or retreat, so to speak. All right. The loss of ice by a glacier is called ablation, and there's two main ways it can happen. The first is just through melting. If it gets warm, the ice starts to melt, and then the water moves quickly, so it runs away from the glacier. And the other process is calving, and this occurs when large pieces at the front break off. This happens a lot in the sea, and it creates large icebergs. You might have like huge chunks just falling off the front of your glacier. So this is showing us the zones above the snow line, which is where snow doesn't melt. You're going to have accumulation, and then below the snow line you're going to have wastage, and it just depends. Are you having more accumulation or more wastage? Whatever you have is going to determine if your glacier advances or retreats. This is an example of glacial ablation. So at the top we have meltwater coming off the glacier. It's channelized through one of those crevasses. It's going to be moving very rapidly. It's going to be cold, but it's going to be pretty clean. If you've ever been to any like glacial lakes, like Lake Tahoe, California is a glacial fed lake, very cold water. If you've ever swam in it, it's right on the border of Nevada and California in an area that you would think is hot, and it gets warm, but the water is cold, really cold. And they actually have a rule there. It's called the 1-10-1 rule, and it says it takes you 1 minute. Once you get in the water, it takes 1 minute for you to gain full control of your breathing, because you'll be hyperventilating because it's so cold. After 10 minutes, you start to lose feeling in your extremities, and after an hour, you risk cardiac arrest and death. So you don't swim too long in Tahoe. You just go for a little bit and then come on out. But yes, it's very, very cold. And I know because I've been there in the summertime and it was hot outside and that water was freezing. But that's because it's fed right from the glaciers of the mountains there, the Sierra Nevadas. All right, and then this is showing calving. So you have this massive ice sheet entering into the sea, and then chunks of it are going to start to fall off the front. You're saying that, Chris?
Yeah, so the place that I grew up skiing is called the Sugar Bowl because of how hot it is in the winter.
Yeah, and you can get powdery snow, and you can get pulverized rock as well, which can give this sort of appearance of like powdered sugar. This is an image of an iceberg. As many of you probably know, icebergs typically have most of their mass below the water line. So when you're seeing an iceberg, you're only seeing, a small percentage of how large of a piece of ice that truly is. All right, we just talked about this. The glacial budget is the balance or lack of balance between accumulation and loss. If accumulation exceeds loss, your balance grows, your glacier advances. If ablation increases and or accumulation decreases, so if you have less snowfall or increased melt, you're going to have a reduced balance in your budget and your glacier will retreat. Because glaciers are sensitive to changes in temperature and precip, they help to provide clues about changes in climate. When we learn about climate change, we'll learn about how we can look at glacial ice and glacial budgets as part of our reconstruction of ancient climates through what we call proxy data. This is an example of some retreating glaciers. It says about 200 years ago, Bear Glacier extended to the N moraine at the bottom of the image here. And we'll talk about those briefly in a little bit. So since it used to reach all the way here, and it's since been working its way back up this area. All right, now when it comes to glacial erosion, this is primarily what your lab is going to be about, looking at some of the features that are created when a glacier moves across land. Glaciers themselves are capable of great erosion because of the fact that they are just very powerful and massive. Glaciers erode the land in two ways. As a glacier flows over bedrock, it can loosen rocks and sort of freeze them into the glacier itself in a process called plucking. They just go bloop, and they like take a rock and they flow over it. They're like absorb the rock into the ice by freezing around it, and then they just pluck it up and they carry it along with them. Another process that they can do is abrasion. We heard about this process with running water as well. Every single erosional force on Earth is going to erode through abrasion. If you're carrying sediment and you're scouring a channel or rubbing against a bank or a valley wall, you're going to scratch at that bank or valley wall with whatever sediment you're already carrying. So glacial abrasion occurs because all of the rocks and sediment that are embedded in the glacier are going to scratch along the bedrock or the valley walls as they move. Rock debris dropped by melting ice is a jumbled up mixture of different sizes and sediments, and we're going to learn about what those features can form, and there's a lot of different vocab terms for the different ways in which glacial material is deposited. So glacial abrasion itself can produce a few things. It can produce rock flour, which is what I just described. So this is the pulverized rock. So imagine like you're sanding something in the wood shop and all of the little dust, that's essentially what's happening here. If you're rubbing two rocks together, it's going to create dust particles that are made of just pulverized rock. It can also produce glacial striations, which are grooves or scratches in the bedrock. If you've ever been to Central Park in New York City, there are some very large boulders there. They're placed by glaciers during last glacial maximum, and you can actually see some of those striations. So like sometimes people climb up on top of the big boulders, and if you sit, you'll see these like deep scratches within. That's the glacial striations that are described here. Glacial erosion is going to be controlled by how quickly the glacier is moving, how thick the ice is, the types of rocks trapped in the ice, and how easily erodible the underlying surface is.
One thing I've noticed, because in the Jugtown Mountains, there's a like every winter, sometimes the ice will freeze over the rocks, and you'll see colors like mixed in with the water, and those are like the mineral deposits that are in the rocks that are visible.
Yep, that definitely can occur too. So this is showing us some of those same abrasion marks that I showed. So you can have the deep grooves, or you can have like a polishing because of all that abrasive action, just like any sandpaper would polish. And then there's what we can see is some of the rock flour, some of that pulverized rock. It can make the water a little bit lighter like this, and you can see some of it near the front. Alright, now when it comes to the landforms that are created by glacial erosion, we're going to talk about a few different ones. Now, when we talked about rivers, we talked about how rivers primarily work by down-cutting land. So when a river carves a valley, it creates a V-shaped valley, a very steep, narrow valley with steep sides, like the shape of a V. And my reminder was river has a V in the middle. This is how you remember they make V-shaped valleys. Now, glaciers make U-shaped valleys because glaciers are much wider than rivers, and their erosional power isn't focused just on down cutting. It's going to be cutting down and along the sides kind of equally as the glacier advances. So while ice sheets themselves tend to subdue topography, valley glaciers can actually increase different formations to make the topography a bit more varied in an area. So the U-shaped valleys that are created by glaciers are also known as glacial troughs. If you call them U-shaped valleys, that's fine. Glaciers tend to straighten out valleys, removing sharp curves, and then they can create something called truncated spurs. We'll look at a picture of that shortly. Glaciers in the main valley typically erode more than tiny tributary glaciers, which can create something called hanging glaciers. So we'll look at all of these in an image. I think will make it a little bit easier to understand. So right at the top there, we have a steep, narrow-sided, or a narrow, steep-sided valley, a V-shaped valley. And then a glacier starts to form in this area. And it's going to widen out and round out that valley, so it gets this nice, wide glacial trough here. And we have this main or trunk glacier here, and then we have some tributary glaciers feeding in, just like they would with a river system, very similar. Because the glacier here is much larger, it's eroding more effectively. So that means that once that glacier disappears, it leaves behind this wide trough, and then these areas where the smaller glaciers were feeding into the central glacier, they didn't erode quite as effectively. So that is why they're sort of hanging up above the rest of the valley. Does that make sense? So that's kind of how that can occur. And these are known as the truncated spurs, where it kind of got cut off by that main glacier as the smaller ones were feeding in. We're going to look at some of these other features as well, arêtes, horns, and cirques. We're going to see all of those in your lab tonight. This is a U-shaped glacial trough. Glaciated valleys can then form something called a paternoster lake. This is going to form when parts of the bedrock that were lifted up and plucked away by the glacier get filled in with water. Something you'll see in your lab tonight is a cirque. This is a bowl-shaped depression typically found at the head of a glacial valley. So sort of where the glacier first forms, it creates a sort of like ice cream scoop out of the side of the mountain. Once the glacier has melted, the cirque can sometimes fill with water, creating a different kind of lake called a tarn. I don't think I asked you on your exam to know all the different types of lakes that glaciers create, because there's many types. But mostly the features that are in the lab are the ones you'll need to be responsible for knowing. When two glaciers exist on opposite sides of a mountain, the dividing ridge erodes away, creating a gap called a col. Sometimes features form from continued glacial erosion of cirques, and this can create an arête and a horn. An arête is a sharp-edged ridge. So this is my best example I can give you for these ones. Imagine you just bought a new half gallon of ice cream. It's pristine and flat. You take your ice cream scooper and you scoop out one scoop. Okay, you just created a cirque, a little bowl-shaped depression. Now, if I took that same ice cream scooper and I wanted to scoop a second scoop, but I wanted to scoop it independent of the first, so I moved my scooper right next to the first one and made a second scoop. Now I have two little scoops, and right in between I have a thin ridge. That's the arête. If I scooped a third scoop on the other side, making like a triangle with my three scoops, I would have a little peak in the middle. That would be my horn. So that's kind of what they're gonna look like. This is the Matterhorn. So imagine that this used to be one flat surface. I took my ice cream scoop, I scooped out a scoop here, I scooped out a scoop here, I scooped out a scoop on the back, and I have this pyramid-shaped peak at the top where those three scoops all meet. Each of the individual scoops would be a cirque, and then the horn would be in the center. And if you look here at this image, it also shows you the arêtes. So we have our scoops here and here, and then the ridges in between, that would be our arête, or our ridge. All right. Another thing we have are something called roches montagnais, which are asymmetrical knobs of bedrock produced by continued glacial erosion. This happens because the glacial abrasion is going to smoothen the gentle slope facing the oncoming glacier, and then it plucks from the back end, so it creates sort of this like asymmetrical mound on the ground. This should be a J, this should say fjords. Fjords are deep-sided inlets of the sea. They're drowned glacial troughs that form when sea level rises. Depths can exceed 1,000 meters. Glacial lakes and fjords are really deep. The Finger Lakes in New York State are glacial lakes. If you've ever been to them, they're very narrow. So if you're looking across, they're only maybe like a mile across, but they can be thousands of feet deep because they're just carved by glacial erosion. So they're these like really, really deep, but relatively narrow lakes. They freak me out because, you know, I'm a good swimmer, but I was thinking about taking my kids there on a boat, and I'm like, what if they slip out of their life jacket and they fall in there, and then, you know, they sink 500 feet under the ground, under the water in 2 seconds. So this is an example of the roche montagnais. So in this example, the glacier would have been coming from this direction. So on the front end, it just kind of gradually goes up the hill. It's going to abrade it and smooth it out. And then on the back end, it's going to pluck away some of those rocks, creating this asymmetrical shape, just like we observed here. And these are the fjords. These are in Norway. So you can see they're not very wide, but they're very, very deep. All right. Okay, so erosional features we're going to look at for glaciers are going to include U-shaped valleys, cirques, arêtes, and horns. Those are the ones you'll see in your lab tonight. Now we're going to move into what happens when the glacier puts down the material it's carrying. That would be depositional features. So glaciers deposit sediment in a couple of ways. As glaciers melt, the rocks and sediments in the glacier are deposited. Glacial drift refers to all sediments of glacial origin. However, depending on how the sediment is deposited, it can have different names. So glacial drift means it came from a glacier. This sediment was produced by a glacier. Two types of glacial drift include till, which is the material that is deposited directly by the ice. Think of this as when the glacier pushes through land, think of it like a bulldozer or a snowplow. It's going to just push all that sediment in front. That's till. Stratified drift is going to be the second type. Stratified, we know, means like layered, or in this case, sorted. So when meltwater near the front of the glacier carries some of the sediment, it is then going to get sorted, with larger pieces being dropped off first, smaller pieces being deposited later. Till is not going to be sorted because it's just all dumped off together at one spot. But if meltwater, liquid, fluid water, is moving through that till, it would change it into stratified drift because it's going to sort it out with bigger pieces closer to the glacier. So based on this, glacial till is an unsorted mixture of many different sized sediments. A close examination of glacial till can often reveal that the larger pieces are going to have those scratches that we talked about, where they were dragged along the bottom or scratching against other rocks. Till is deposited as glacial ice melts and drops its load of rocks. You can also have something known as glacial erratics. These are boulders within the till or lying on the surface. These boulders can be huge, massive, really big. So they're called erratics because they do not match with their surrounding geology. So if you're like out in a field somewhere and all of a sudden you see some like big rock and you're like, well, what is that even doing here? That's so weird. That looks so out of place. That's so erratic, right? It's probably a glacier just brought it there and dropped it off. So they usually look very out of place. You don't have to be a geologist to see like, oh, that looks weird. Why is that giant rock just here in the middle of this field where there's no other big rocks? Or why is this rock that looks so different than every other rock plopped here in the middle? Probably a glacier just brought it there and dropped it off. Stratified drift is sediment sorted by size and weight. We know that the larger particles will be dropped first and heavier or lighter ones will be carried further. That is going to be deposited by the melt water, not directly by the glacier. So even though it's all drift, stratified drift is carried by meltwater, till is deposited directly from the glacier. So I need to know those differences. This is a glacial erratic. Big old rock in the middle of this forest. Where'd that come from? Oh, a glacier came through and dropped it there. All right, now we're going to talk about some of the landforms that are created by glacial till. The first are going to be moraines. So moraines are essentially just piles of glacial sediment. and there's a few different types. A lateral moraine is an accumulation of debris on the side of a glacier. That's what lateral means. A medial moraine is going to be in the middle of a glacier. So when two glaciers converge, what would have been their lateral moraines are going to combine into one medial moraine in the middle of those two glaciers. And then we can also have terminal moraines or end moraines, which are deposited at the front of the glacier. So this is an example. So the moraine is just a big pile of dirt, basically, that the glacier is pushing around. So again, think of a bulldozer or a snowplow. If it's on, you're starting out, it's gonna build up sediment or snow or whatever along the sides. If you're carving through the front here, you're gonna have like built up piles on the sides. You're gonna also have built up piles on the front. So that's what the moraines are made out of. So here we have, it's a little easier to see here. We have two glaciers. We have a sort of a main glacier here. We have a tributary glacier here. As this tributary glacier feeds into the main one, what was its lateral moraine now is going to be at the center of this larger glacier to create a medial moraine right in the middle. So big medial moraine here, lateral moraines off to the sides. We said that glaciers are similar to a conveyor belt in how they move. Regardless of the movement, sediments are constantly being pushed forward and dropped at the terminus. The end moraine is an accumulation of debris that forms at the terminus of the glacier. This is the pile your plow pushes forward. The glacier will retreat to a point where it's in balance, and then it will form a new pile. So you can see what is known as the terminal end moraine, which marks the furthest point of advance of the glacier. And then you can see what are known as recessional end moraines, which show, okay, here's the stopover points the glacier made between the furthest point and where it exists now. And every time it kind of stabilized, it started to form a new moraine at the base of the conveyor belt, and then it may be moved back later on. They're showing some of the end moraines around the Great Lakes. Long Island is a terminal end moraine from a glacier from the last glacial maximum. So just a big old pile of dirt that a huge glacier pushed together, and now it's Long Island. Some other features that we can find created from till include drumlins. These are streamlined asymmetrical hills composed of till formed from ice sheets. Again, I'm not going to quiz you too much on all these specific features, but just be mindful that some of them might come up in their definition. These are what drumlins look like, tiny little hills. Two basic categories of features composed of stratified drift include ice contact deposits, which are right next to the glacier, and then outwash sediment, which is deposited further away. In outwash plains and valley trains, glacial meltwater that gets choked up with sediment can flow onto a flat surface, drop its load, build up a broad ramp, and then create braided streams. Outwash plains are associated with ice sheets. Valley trains are associated with mountain valleys. Same kind of general idea. Meltwater itself is going to flow over, within, and at the base of motionless ice deposits. Stratified drift that remains once the ice melts away, or stratified drift will remain once the ice melts away. A kame is a steep-sided mound formed from ice contact in stratified drift. Esker is a narrow, sinuous ridge made of mostly sand and gravel. Again, I'm not going to ask you all of those features. These are all things that a glacier can also produce. Eskers, drumlins. Here we have a braided river, so meltwater from the glacier is going to move forward. It's going to cut through some of the sediment that was deposited, and it's going to carry with it stratified drift, which will be dropped off in accordance with its size and weight. Okay, so that kind of sums up the main erosional and depositional features we're going to look at for glaciers. Now we're going to talk about some other things that glaciers can do. Ice sheets themselves are pretty heavy, obviously. It's like hundreds of meters worth of ice. That weighs a lot. So they can cause down warping of the crust. After glaciers melt away and that pressure is relieved, the crust can start to rebound. It's not going to move as quickly as it would during like an earthquake event. We talked about like elastic rebound hypothesis. So it will still rebound. It's going to probably rebound a little bit more slowly, not as dramatically as during an earthquake event, but the same process will occur. The ground will no longer be strained under all that weight, so it'll start to go back to its original form. Sea level changes are also going to occur as a result of glaciation. If we have a lot of glaciers on Earth, then we're not going to have as much water in the ocean because we only have so much water on Earth. If it's not in one reservoir, it's in another. So if it's not in the oceans, it's in the glaciers, or it's in the sky. If it's not in the glaciers, then it's going to be in the oceans. Right? During the last glacial maximum, sea level was approximately 100 meters less than present level. The Atlantic coast of the United States, therefore, would have been more than 100 kilometers east of New York City. So we would be a lot further from the beach if that were the case. If the Antarctic ice sheet melted, sea level would rise somewhere between 60 and 70 meters. That's very problematic because a lot of people on Earth live very close to coastlines. So an increase like that, 60 to 70 meters, it's going to be very substantial, especially for areas like ours in the eastern United States. We have very gentle sloping beaches. Our beaches are very flat, so we are very sensitive to changes in sea level. On the west coast of the United States, where the beaches are a little bit more jagged and the whole topography of the area is more rugged, the coastlines are a lot steeper, but here in New Jersey, our coastlines are really shallow, so if water rises, it impacts us a lot on this side of the country. This is showing some subsidence and rebound. So the crust is downwarped when there's heavy ice on top. Once the ice is removed, the crust goes back to normal. This is showing you what coastlines would have looked like here in the United States during the last glacial maximum, so about 18,000 years ago. So again, you can see like the Gulf is a lot smaller, a lot reduced in size. Look how minimal the difference is on the western United States as compared to the eastern United States. So when it comes to climate change, we in the East Coast and the coastal states, we are really going to be at significant risk if sea level rise continues at the rate it is going to continue. There's less risk for the western states because they're not as easily impacted by changes in sea level. Advance and retreat of North American ice sheets can also change the routes of rivers. We're not going to learn too much specifically about the Mississippi in general, but you know, it's there if you want to do some research. New York's Finger Lakes, I told you, those are some of our glacial lakes. Super narrow and really deep. That's what they look like. Other issues that we can have, ice sheets and alpine glaciers can act as dams to create proglacial lakes. We talked about how ice jam floods can occur, so the same thing can occur with glaciers. We can have lakes at the front of the glaciers, and if the ice dam fails, it can release a lot of water very quickly. We also have something known as pluvial lakes. The growth of ice sheets can cause temperatures and evaporation rates to decrease in semi-arid regions, and then if precipitation does occur, it can form something called pluvial lakes, like we have here in the western United States. Alright, glaciers were once more extensive than they are today. If we look at glacial deposits using the principle of uniformitarianism, we know, okay, I see that these are moraines and I can see that they extend way further than where glaciers exist today, so I know glaciers must have been a lot further out than they are today. Glacial and interglacial cycles typically occur every 100,000 years. The northern hemisphere ice ages began between 2 and 3 million years ago, and we've had approximately 20 of the cycles of glacial and interglacial. The Antarctic ice sheet formed at least 30 million years ago. So currently we are in an interglacial period. So historically we would anticipate temperatures to get cooler and start moving more towards increased glaciation. But it's being counteracted by human-driven climate change. So it's not exactly what we're observing, even though that's what we would have expected to observe. The Quaternary Ice Age is not our only ice age, however. We've had ice ages before. They can occur for a variety of reasons. And we're going to talk more about some of these reasons in climate change as well. But tectonics is one reason ice ages can occur. As continents shift and move, it can change circulation patterns in the ocean, which can change how heat is distributed around Earth. If continents move towards the poles, it can lead to glaciation. Like I told you, we need land in polar regions for glaciation to occur. So in instances where there's no land in the polar regions, we're not going to have those massive ice sheets. Climate change triggered by tectonics is very gradual. It's going to happen on millions of years, right? Because the plates move very slowly, as we know. Other issues or other possible reasons for glaciation are variations in Earth's orbit. And if you've ever talked to someone who doesn't believe in human-driven climate change, they might bring up these ideas to you about variations in Earth's orbit and how it impacts the amount of solar radiation that we receive, and it affects temperatures on Earth. And that's true, and these are measurable and predictable. We're going to learn a little bit more about them in climate change. But these 3 cycles are called the Milankovitch cycles, and they have to do with the way in which Earth moves through space, and it changes periodically. So the first has to do with Earth's eccentricity. Eccentricity is a measure of how circular or oblong your orbit is around the sun. If you have an eccentricity of 0, it means that your orbit is a perfect circle. Earth's orbit is not perfectly circular, it's pretty close, but there are periods of the year where Earth is closer to the sun and further from the sun because it's slightly oblong. So for us, the Northern Hemisphere residents, we are actually closest to the sun during our winter and furthest from the sun during our summertime. But that can change. The Earth's eccentricity can change slightly, so there are times where our orbit is more circular and times where our orbit is more oval. The other cycle we talk about is obliquity, which is changes in the angle of Earth's axis. So currently Earth's axis is angled about 23.5 degrees from perpendicular, but that can vary from like around 25 degrees to around 23 degrees. So the Earth kind of goes back and forth like this on its axis, and the more dramatic our axis's angle is, the bigger variations we're going to see in polar regions to equatorial regions. If there's less of an angle, you would see less variation in the polar regions and the equator. You'd still have colder temperatures at the poles, but you're not going to have seasonal variation. Yes?
Like, doesn't it occur in such a long scale that if it were to be like why we were moving towards like or why our climate was warming, that it would be too gradual to even notice in the first place?
Yes, pretty much. So yes, like these cycles, they're not to be discounted. There's been natural climate changes throughout all of Earth's history, but the current changes that we experience now way outpace anything that nature would have produced. And that's how we know. Like, it's not really a question if humans are causing climate change. It's just, it's known fact, and it's been known for decades. Like, people like to pretend, not people. We'll talk more about it next week, but it really riles me up. So we'll talk more about, there is a massive misinformation campaign around climate change, and it is not the consumer's fault. There is literally just propaganda designed by corporations, and I personally have firsthand observed it. So it's not the public's fault for being confused about the issue. It is very carefully orchestrated confusion. So we'll talk more about that next week. But the last Milankovitch cycle is known as precession, and this is the wobbling of Earth on its axis, and this one's kind of confusing. But Earth, it's tilted like this, and it spins every day, but it also kind of wobbles around like this. So imagine a spinning top as it's about to fall, it starts that little wobble. Earth does that. So right now, Earth's North Pole, it's pointed right at the star called Polaris, the North Star. But because of the fact that sometimes we wobble around, we make like a little circle in the sky. So there are times where the North Pole is not in line with Polaris. It's not in line with the North Star because it would be in line with some other star in the sky, which would then be the North Star in that instance. So that's another cycle that can impact climate as well. So because of this, we can have changes in solar input, solar radiation, which affects temperature, which then in turn affects ice age. And these are all the pictures that I just showed you with my hands. So the top one, this cycle takes about 100,000 years. It goes from nearly circular to slightly more elliptical, then back again. This diagram is really exaggerated to just show you the idea. It's not that dramatic of a shift. Here we have obliquity, so how tilted is the planet, anywhere from 21.5 to 24.5. This cycle takes about 41,000 years to complete, so going from one to the other. And then precession is that spinning of the top. Earth's axis wobbles. It takes about 26,000 years for this cycle to complete. So right now where we're positioned, like I said, the North Pole points right towards the North Star. When we're at the other end of our extreme in precession, we point towards Vega. So that would be our North Star at that time. Other factors, changes in Earth's atmospheric composition, of course, are going to influence climate and therefore glaciers. Changes in ocean circulation, changes in reflectivity of Earth's surface, which we'll talk more about next week as well. This is showing you an ice core. We talked about taking rock cores or sediment cores when we did that packet on relative dating. So we learned like, okay, they insert this instrument into the ground and they take out a sample. It almost looks like a tennis ball canister. They shove it into the ground, they pull it out, and then they have like a nice tube with all the records of the sediment preserved. The same thing can be done with ice. We can take the same types of devices, we drill a hole, we kind of collect this ice in a nice long cylinder, we slice it in half, we open it up, we look at it, and it contains a lot of information. Ice can trap pollen from hundreds to thousands of years, so we can see what kind of plants were prevalent at different times. It can also trap actual pockets of air, so we can see the composition directly of preserved atmospheres from earlier. And we'll learn more about all of the data that we can collect from ice cores next week.